Hello, in this second video on integration by parts, we will be looking at what is called a cyclic example. So this is a difficult topic, but let's give it a go anyway. So we've got a familiar looking problem here. We've got the integral of the product of two functions, namely e to the minus x and cos of x. So we're doing by parts because we have a product of two unrelated functions. So we'll be using the following formula, that the integral of u times dv by dx is the same as ub minus the integral of v du by dx. And our first job, as always, is to find out what should u be. Well, let's go through our hierarchy of logs, algebra, trigonometry and exponentials. There's definitely no logs there, there's definitely no algebra, so we'll take trigonometry to be our u function, specifically cos x. So that must mean dv by dx is e to the minus x. Let's do some trigonometry now, and trigonometric differentiation, some exponential integration. The derivative of cos of x is minus sine x, and e to the minus x would integrate to negative e to the minus x. We're now in a position to substitute into our by parts formula. I for integral equals u times v minus e to the minus x cos x. Take away the integral of du by dx times v, so that would be minus e to the minus x times minus sine of x. And let's just tidy up these negatives. We've got two negatives, so that will make it positive. We've really just got e to the minus x times sine of x. Okay, we've transformed the integral. We've still got a very challenging integral here. In particular, this one here. But we can recognise the form. It's the product of two functions. So if we integrate here, we will get, well, we need to write out what u equals, what du by dx is, what dv by dx is, and what v is. So we'll just approach standard strategy. We'll go for hierarchies. There's still no log terms, still no algebra, but there is a trig function of sine of x. So u must be sine of x here. And therefore dv by dx will again be e to the minus x. Let's do some differentiation. Sine differentiates to positive cos. E to the minus x again will integrate to minus e to the minus x. And for the second time, let's do an integration by parts. We will get the integral equals, let's write that a little bit neater, I for integral, e to the minus x cos x minus, and then u times v, so minus e to the minus x sine x, and then du by dx times v, so that will be minus the integral of minus e to the minus x times cos x, and then we can see that, well, we've got a lot of negatives here. Let's just tidy those up a little bit. I've got two negatives there, that will be the same as a positive. Let's expand out on the next line. I will get the integral I equals e to the minus e to the x cos x. Two minuses make a positive. And then minus that integral there. So how have we done? Well, we've still got a very challenging integral here. However, I think we've gone round in a big circle. that integral there is exactly the same as the integral we wanted to work out. So we can call that the integral which is trying to find equals this expression here, and then take away that same integral. So now, to solve this integral problem, we're actually just going to solve an equation for I. We'll add that I to both sides to get 2I equals minus e to the minus x cos x. And then divided by 2, the integral would be minus 1/2 e to the minus x times cos x plus 1/2 e to the minus x sin x, which is an answer we are happy with, plus c. So that completes our cyclic example. The thing to look out here is, if you've done integration by parts a couple of times in the same question and you feel like you're not making progress, try and get the actual question in your answer and then solve for that variable. Lovely. So you've got an example to have a go at underneath to practice that concept. I'm now going to move on to a definite integral example. So in particular, we'll have a look at this question here. Question 36, where we've got a definite integral, and we know it's a definite integral because there are now limits of integration. So we'll approach it as normal, but pay particular attention to looking at what happens to the limits during our process. So this is an integration by parts question. We can see that this is a product of two functions. So we'll be using the formula in the following book, which is the integral of u dv by dx equals uv minus the integral of v du by dx. Okay, so we need to choose what u is out of these two terms in our product. Well, we've got two expressions. Let's go through our hierarchy. We've not got any logs. Oh, we do have logs, I beg your pardon. So we're done. We've got a logarithmic term. So log of 2x must be u, and therefore the other term of that product must be dv by dx. We'll do some differentiation. 2x log of 2x differentiates to 2 over 2x, or 1 over x, and 2x squared would integrate to 2/3 x cubed. Lovely, so now in a position to integrate. I'll use again I for integral. So this will be uv log 2x, and I could put times 2/3 x cubed. We don't normally write it that way round. It's a little bit neater to instead write 2/3 x cubed log of 2x. And then take away these two times together. So that would be an integral 1 over x times 2/3 x cubed would be 2/3 x squared. And I'll look where I put the limits for this now. So on the one hand, those limits will still apply to this modified integral, and they also need to be substituted into this term, which I'll just use with a square bracket. Okay, we'll come back to those limits. We've got an integral to do though first. So I'll have 2/3 x cubed log of 2x, and then minus, what do I get when I integrate 2/3 of x squared? I will get 2/9 of x cubed. And then, I still need to put those limits in. This time I'm going to go for a bracket around that entire expression to 1, like so. And now in a really familiar position, we just need to substitute in. So we'll get 2/3 times 2 cubed times log of 2 times 2 minus 2/9 of 2 cubed again. Take away, I think I can do this one in my head, 2/3 of 1 cubed times log of 2. Take away 2/9. Okay, you could type this into your calculator, but you'll get a decimal answer. So let's try and manipulate this just using our log knowledge. I'll just make some space by crossing out that example that you can have a go at later. Let's do some arithmetic. So 2/3 times 2 cubed, that's 8 times 2, so that's 16/3 times log of 4. 2/9 times 2 cubed is minus 16/9. And then minus 2/3 log of 2. And then taking care of this double negative plus 2/9. Okay, can you see how we've got a different argument for those logs? We want them to be the same. So I'm going to rewrite 4 as 2 squared, because now I can use the power rule to bring that power down to get the following expression. 16/1 times 2 will be 32/3 log 2. Minus 16/9, add 2/9 is minus 14/9. Take away 2/3 log 2. And now that these arguments of the log are the same, I can just collect like terms. So I've got 32/3, take away 2/3, that would be 30/3 log 2. Still got this minus 14/9. And we can simplify even more. 30/3 is indeed 10. Lovely, and that concludes that example. I think there's 2 nice things that we can reflect on there. The first is where these limits go, as we do in integration by parts. And then secondly, linking to get an exact answer by using our knowledge of logarithms, in particular our use of a power rule here.